So welcome to this week's Origins Colloquium, actually the second one this week. So it's a pleasure to welcome our own Gina Panapopoulou to give the talk this week. Gina received her PhD from the University of Crete in 2017, and I think you were working on magnetic fields at that time as well. Maybe we'll hear a continuation of that work. She got a postdoctoral position at Caltech, including Hubble Fellowship, so the most prestigious postdoctoral fellowship in the US system, and was there for 5 years. In fact, I think we had lunch there before you arrived here as an assistant professor in 2023. And she's been here then a few years and already building a large group here and also supervising a couple of projects in the CASM program this summer again. So welcome, Gina. We look forward to your talk.
Thank you, Jonathan. Hi, everyone. You'll be seeing more of me this summer, hopefully. So what I'd like to discuss today is our efforts in trying to map the galaxy's magnetic field in 3 dimensions. If you have pressing questions, feel free to interrupt me at any point in the talk, and we'll try to make this a discussion. So magnetic fields are everywhere in the universe. We know that the universe is filled with, ionized plasmas. I forgot I have an outline slide. So actually what I'm going to talk about is that, our motivations for mapping the magnetic field structure, and then looking a little bit at the tools that nature gives us to do that. And finally, I'll tell you a little bit about what we're learning about the magnetic field around the sun. The ISM in the vicinity of the sun. But okay, let's move forward. So yes, magnetic fields are everywhere in the universe. Plasmas permeate the universe, and so we know that in different systems, magnetic fields play different roles. So for example, if you look at supernova remnants, that's where magnetic fields help accelerate particles to relativistic speeds. And that's how you get cosmic ray acceleration. If you go to the other end of scales, looking at the environments around supermassive black holes, we know that magnetic fields help to remove angular momentum from the system, allow gas to collapse into the black hole, and they shoot these powerful jets that move material way far away from the centers of galaxies, right? So thankfully we have magnetic fields to, look at these wonderful systems and learn about the physics. Now in the ISM, magnetic fields are somewhat special. They have an energy density that's comparable to the other energy densities of the different components of the ISM. So if you look at the magnetic energy density, it's order 1 eV per cubic centimeter on the mean diffuse ISM. And that's same order of magnitude as thermal energy from the hot gas, the kinetic turbulent energy, that of the cosmic rays, you name it. So what this means is that magnetic fields are potentially dynamically important in the ISM. If you look here on the right, that's an image of a nearby molecular cloud, a torus molecular cloud that Mo is working on actually for the summer. So in this star-forming region, what we see with observations from the Planck satellite is that magnetic fields form these very ordered patterns that you see projected on the sky. And this means that they are dynamically important. They shape the formation of these filamentary structures. They affect the way that the gas collapses to form stars. So magnetic fields in the ISM are special, but we really don't know how special they are because the importance of the magnetic field varies with conditions. So what I'm showing you here on the right is a plot from a simulation where they've taken a Milky Way type galaxy, evolved it to, from cosmological initial conditions, evolved it to Z of 0, redshift of 0. And inside the simulation, there's feedback, there's heating and cooling, there are cosmic rays and magnetic fields. And here you're seeing the different components of the ISM of that simulation. So y-axis is energy density or pressure of those components, x-axis is the density of the gas. So what you see is if we select regions in the solar circle of this Milky Way type galaxy within 1 or 2 kpc from this midplane, and in that box that I'm showing within a few particles per cc density, that's where all those lines cross. So the thermal pressure, the dotted line, the dotted dashed line, which is the cosmic rays, and the orange line, which is the magnetic field, all have the same, pressure over there. But if I go to lower densities or higher densities, if I go near the center of the galaxy, that balance is bound to shift. This is a simulation. We don't really know what happens in reality, so we need observations to tell us what the energy balance is as a function of scale, environment, condition, you name it. Okay, so observational. The best tool, I would argue, that we have to judge this energy balance is to map the geometry of the magnetic field. Now, the reason is the geometry encodes a parameter that tells us about the energy balance between the kinetic turbulent motions and the magnetic pressure. And that parameter is called the Mach number. You can see it right there. It's basically the ratio between the velocity fluctuations in the gas and over the speed at which magnetic perturbations propagate in the ISM. That's the speed. So if you have this number, the Mach number, be smaller than 1, that means the magnetic energy is more dominant than the kinetic energy. You have a situation like that on the top right, where the magnetic fields are straight and parallel and basically guide the flows of the gas. So these are, on the right, 2 images of a different type of simulation where you have a box of an isothermal gas, you're driving turbulence on large scales, and you have periodic boundary conditions. So very different type of simulation, but allows you to look at more detail of the formation of the structures and the revolution. Okay, so the top panel is for Mach number smaller than 1. That's the regime of sub or transalphanic turbulence, that we say. Bottom panel is for superalphanic turbulence. That's when the kinetic motions are so much stronger than the magnetic field that they jumble up the magnetic field lines. Magnetic field lines appear all tangled in that bottom right panel. So you can see by eye, different magnetic field geometries mean different things about the energy balance. Okay. So hopefully, yes.
Out of curiosity, do the fields amplify in this bottom right so that this is just a snapshot in time? And the
There's no dynamo in these simulations, if that's your question.
So when you do driven turbulence, the field doesn't amplify?
Well, it would for adiabatic, like compression, yeah.
Okay, maybe we can come back to that, but...
Yes, they probably... Yes, if you're compressing the gas just from flux raising, you would increase the field in these cases.
Okay, but anyway, at a given snapshot, they can measure what is the instantaneous alpha Mach number.
Yeah, averaged over the whole box, for sure. Yeah, locally, you could have a difference. Okay, so by mapping the magnetic field geometry, what we hope to do is try to understand how the ISM and in general the magnetic field evolves. And we know that there are a bunch of different processes involved in affecting how magnetic fields are shaped. On global, galactic scales, there's galactic rotation that we think is responsible for forming these very coherent patterns that align with spiral arms in this M51 galaxy. On smaller scales of hundreds of parsecs or so, we expect stellar feedback to play an important role. For example, what I'm showing you on the right is an image of a nearby superbubble in the Milky Way, where the collective effect of supernovae, young stars, has evacuated a cavity in the ISM and is forming, causing the magnetic field to drape around that cavity. So you're seeing this loop-like structure on the right here. So that's what we're hoping to get at, mapping the magnetic field geometry across scale, across environment. How do we do that? Well, nature gives us several tools. So here, I'm going to tell you a little bit about the different mechanisms that we can use to measure the magnetic field in the diffuse ISM and predominantly for mapping the geometry. There are other probes that I won't mention, but you can ask me about them later. So first off, we have synchrotron emission. That's the emission that's produced by relativistic particles, electrons in this case, spiraling around the magnetic field lines. This emission is polarized in the direction that's perpendicular to the local direction of the magnetic field. So when you measure this emission, you'll see the collective effect of all these cosmic ray electrons, that's their density over there, multiplied by the strength of the magnetic field projected on the sky, raised to some power that has to do with the slope of the energy spectrum of the electrons, and integrated along the line of sight. There is a map of this kind of emission from Planck. You can see it here. The colors show you the strength, so the intensity of the synchrotron emission. The lines show you the inferred magnetic field projected on the sky from the polarization of that emission. So this is our first 2D map of the magnetic field in the Milky Way that I'm going to show in this talk, and there are 2 more. You can see various features that we can talk about, but for now, let's move on to the rest of the probes of the magnetic field. The next probe is polarized dust emission. Now, you know that there's dust in the ISM. Particles that are of order 0.1 microns and a little bit larger, they are typically aspherical, and they get aligned with their short axis parallel to the magnetic field lines, as shown in this cartoon. The E vector of the thermal emission of these dust grains is polarized perpendicularly to the projection of the magnetic field. So when you measure the polarization of this dust emission, you can map the magnetic field projected on the sky. But this time, your signal is an integral along the line of sight that has some function that weighs in the temperature of the dust grains and their microphysical properties, like the porosities, the shapes, things like that, compositions. You also weigh by the density of these particles. And there are these 2 factors here that tell you about the geometry of the magnetic field. So gamma is the angle that the magnetic field forms with the line of sight. Theta is the angle that it forms on the plane of the sky. So the second map that I want to show you, again, a 2-dimensional map of the magnetic field, but now measured by the polarization of dust emission from Planck. You can see a lot more detail, higher resolution data at higher frequencies, but still you can see some same qualitative features similar to the first map from the synchrotron, which is that the magnetic field in the midplane is typically parallel to the disk, and outside of the plane at high latitudes you have these features that shoot out from the plane. Okay, so up until now we have 2 probes that tell us about the plane of sky component of the field. The third one that I wanted to show you is Faraday rotation. This tells us about the line of sight component of the field. So if you have linearly polarized light, which propagates in a magnetized and ionized medium, it will acquire a rotation of its polarization plane, which is proportional to the wavelength of that light squared, times this integral that now weighs the density of the thermal electrons with the line of sight component of the field. And of course, it's a line of sight integral as well. So let's look at a Faraday rotation map of the galaxy. This is what it looks like. Blue tells you the magnetic field is on average pointing towards the observer. Red tells you that the magnetic field is on average pointing away from the observer. Okay, so now we have these 3 different measures of the magnetic field, different components, weighted by different phases of the ISM. It's a mess. But somehow we have managed, or at least people have managed, to construct models that are consistent with all of these 3 observables. So here what you're seeing are 3 models of the magnetic field of the galaxy. We are an observer placed above the center of the Milky Way looking face down on the midplane. Colors show you the strength of the magnetic field. Arrows show you the local direction. And just by staring at these maps, you can see they don't really agree. One doesn't have spiral arms. The 2 that have spiral arms disagree on all the details. And the reason why we're stuck with these really uncertain models is because we've been using 2-dimensional data to constrain them. And these 2-dimensional data don't really discriminate between things that are projected large on the sky but are nearby the sun versus large-scale features of the galactic disk. Question, yeah.
I'm not sure if this is like a dumb question, but how is it possible that on the inside of the spiral, the arrows are moving in one direction and then on the outside they're moving the other direction?
how is it possible? It is a very difficult question to answer. But it appears from these kinds of observations here that this is necessitated. You need to have some kind of reversal of the magnetic field when you cross from one spiral arm to another. Now, whoever creates the models says this is necessitated or isn't. There are models that don't show this feature, but at least one of the reversals is universal in all of the models, and I forget which one it is.
So these are three different models.
Different models.
So maybe we can discuss later, but they have different boundary conditions or something, because they're using the same input data.
There is no input data. These are
Sky
like
map.
analytical models, right?
They take the 2D sky maps.
Yes, and they're constrained with the 2D sky maps.
Yeah.
So you put in some azimuthal component, some halo component, and you try to fit that to your data.
And they require div b is 0 or not?
Some require div b 0.
Oh,
Not all.
okay.
Yes, why you have reversals is kind of unclear, but good question. Okay, the situation isn't great, but we can move forward and we can do better things. One of the most recent works that highlights this problem is the work by Unger and Farrar that I'm showing you here. And what the authors did was they took their default model, which is on the left. Again, this is a projection of the midplane. The colors show you the strength of the magnetic field in their model. That's the component that's in the disk. And you can see in this model, the magnetic field alternates from clockwise to counterclockwise. The sun is this star over here. The galactic center is here. The overlaid points are masers that are used to fit the spiral arms in the galaxy. On the right, what they're doing is they're setting the magnetic field in their model everywhere to 0, except for the local spiral arm. And they say, okay, we have these two different models, one that's just a local feature, one that has global features. What do they look like when you look at the Faraday rotation that they predict? It turns out that they look pretty similar. So what you're seeing here on the top panel is the predicted Faraday rotation from each of the two models in red and black squares, kind of hard to see, and the black dots are the actual observations, higher latitudes, so different latitude cuts basically. Two models, very different structures within them, produce very similar observables on the sky. So that's the problem. How do we solve it? Well, we can look at local tracers of the magnetic field. For example, we can look at stellar polarization, because stars become polarized by the same interstellar dust grains that emit the polarized thermal dust emission that we saw. And in this case, the E vector of the polarization of these background stars is just going to be parallel to the projected magnetic field. Bless you. So when you look at the polarization of many, many stars back onto a cloud, you can make these maps that trace the magnetic field projected on the sky. But now with Gaia, we have distances to each of these stars. So with parallaxes, we can actually tomographically discriminate which stars are behind which cloud along the site. And in a very idealized scenario where you have cold, diffuse clouds along your line of sight, you expect that the polarization parameters that describe the stellar polarization, the Stokes parameters, are piecewise constant functions of the distance. So where you have no dust in the foreground, you'll see 0 polarization of the stars. When you pass a cloud, you'll start to see stars that are polarized due to that cloud. And then when you pass a second cloud, you'll see the cumulative effect of both clouds in the polarization. And this is a vectorial addition, so it's not a simple subtraction of the polarization, but it can be done. So in this very fortunate situation, we can try to isolate stars at different distances that probe different dust structures and see what their polarization is telling us about the magnetic field. We've started to do this for different structures around the sun, and for the rest of the talk, I'll just focus on one feature of the local ISM environment. On the left, I'm showing you this idealized model of the galaxy, which you might have seen before. On the right, I'm showing you an actual 3D reconstruction of the dust distribution that came from inverting the extinctions of stars at known distances. So on the right, we actually have a map, not an input model. So the red colors are showing you where there are prominent dust features in the galaxy. The center of this plot is the sun. Towards the right is the galactic center, and the scale is plus or minus 3 kbc. So we haven't managed to map the entire galaxy yet, but within this volume of 3 by 3 kbc or 6 by 6, we actually know very well the distribution of dust in 3D. The feature that I'm highlighting here is a portion of the local spiral arm. And that's where we wanted to look first to see what the magnetic field is doing. Because remember from the previous plots, that feature seemed to dominate the rotation measures. So let's look at this feature in more detail. This on the left, again, is a face-on projection of the dust distribution, looking at the center, here the sun. These red points are star-forming regions that appear to line up in this very sort of straight-ish line. The straight-ish line has a name. It's now called the Radcliffe wave, and the reason for that is because if you look at it on the side, it seems to have this wavy pattern up and down the midplane of the galaxy. We really don't know what created this pattern yet, but we're trying to understand it. So for now, what I'm going to show you is what the polarization of stars is telling us for the magnetic field and the structure, and focusing first in this really smaller region around the nearest approach of this feature to the sun. Okay, so I'm going to change again our view, and now we're going to go from this 3D to 2D on the sky, which is where all our observables are. So this, on the background, you're seeing the extinction of dust associated with this feature on the sky. The colored line shows you, we go back, if you fit a line to all these data points, you get a squiggly feature. We'll call it the spine of the Radcliffe wave. That spine is projected here on the sky. Blue means very nearby to the sun. Red means far away from the sun. So you can see, it's like, I'm going to theatrically display this. You have this feature that comes along your line of sight. It's very nearby here and then goes away. So you have a very large projection on the sky of the nearby part, very smaller projections at the endpoints. Okay, hopefully the geometry is clear. Okay, so let's look at what the stellar polarizations are doing. The yellow segments are showing you the local polarization orientation of the stars. The dashed cyan line shows you the spine of the Radcliffe wave, and the dashed white line shows you the midplane of the galaxy. And you can see by eye, there's some offset, there's some tilt to the polarizations of the stars. If I make a histogram of the difference between the stellar polarizations and the midplane direction, I see that there's an offset of, on average, 20 degrees. If I compare instead the polarization of the stars with the spine of the Radcliffe wave, I see that there's an alignment. So the offset goes now to 0 on average. So what we're seeing is that the magnetic field in this part of the wave seems to be aligned in projection with the spine of the wave. You might have noticed that there are some selection effects going on here. So I've selected stars only to be within 600 parsecs. That's where the distance at which we are sure that the stars are only probing the Radcliffe wave and nothing that's further away. If I start looking at stars that are really further away, so 2 kbc or more, I see that their polarizations are now tracing a direction that's more parallel to the midplane of the galaxy. And that's more in line with what the synchrotron maps and the dust polarization maps were showing. Okay, So we're fairly confident we've isolated, at least in this part of the sky, what the geometry is doing of the magnetic field. You might notice that there are these white segments that I'm sort of trying to hide over here. The reason for that is we don't think that those are probing the large-scale field of this feature. We think instead they're probing a local sort of perturbation that's caused by a bubble. So here what I'm showing you is the column density of H1 emission at a single velocity of 1.4 kilometer per second. You can see that there's this, I don't know, projection of a loop or something like that. This is known to be some cavity which as yet does not have any remnant associated to it, but it's probably something to do with a supernova, maybe. There's no young star or anything like that, so it's unclear. But the magnetic field in any case seems to be draping around this cavity, so that's why it's not tracing anymore the large-scale component of the magnetic field. This local feedback effect that's destroying.
What's the name of this bubble again?
The percussion.
Yeah, okay, this is the one that Schmoll works on.
Yes,
yeah.
exactly. Okay, so I showed you what happens in this small chunk of the Radcliffe wave. What if we look throughout the entire Radcliffe wave? So here, this is a bit more, contrived figure, which is trying to show us some cumulative statistics. So again, this is showing you the projection of the spine of the Radcliffe wave on the sky. The colors are showing you in each pixel what is the difference between the direction of the polarization and the direction of the spine of the wave. So what we see here is that the polarizations are aligned with the Radcliffe wave. Polarization differences are within 20 degrees or so. If you look towards the endpoints, the colors change a lot, this here and here. And where there are molecular clouds, there's also a big scatter. And this is kind of what you would expect, qualitatively at least, if you were looking at this magnetic field that comes at you and then goes away from you, because you expect to have more scatter along your line of sight than when the magnetic field is projected on the sky. So we think that the magnetic field could be aligned with the Radcliffe wave in 3D. And I'm very fortunate to be working with Siddharth, who's a PhD student here, who's trying to model the magnetic field in 3D of this local spiral arm and try to see how well, if we input different parameters for this 3D alignment, how well does that agree with the data that we have? Okay, I'm almost done, yay. So the underlying question that has been sort of in our minds from this work is, okay, if you have constrained this 3D magnetic field geometry, does that tell you anything about how this came to be? How did the magnetic field form, and how does the Radcliffe wave form? Let's see if that helps. We know that with different theories of how clouds form, we expect different roles for the magnetic field. So if, for example, molecular clouds form predominantly by collisions, maybe driven by supernovae and other type of stellar feedback, you would expect the magnetic field to perhaps lose its coherence over a larger scale. On the other hand, if you have a larger scale magnetic field that's subject to instabilities in the disk, for example, the Parker instability, you expect the flow of gas to be determined by the orientation of the field. And there are predictions for a more larger coherent field that has some oscillatory patterns. So the hope is to try to discriminate between these different kinds of theories for the Radcliffe wave and similar structures in the future. Okay, to do this for a larger chunk of the galaxy, we would like to have more data, as always. And so we're embarking upon an optical polarization survey to measure millions and millions of stars in optical polarization and try to get these three-dimensional maps in the near future. All right, with that, I'll summarize. hopefully you've learned something about how we can map the magnetic field geometry in the galaxy at least. It's a cool thing to do because we can learn about the ISM properties, maybe how clouds form, how the ISM evolves, how the magnetic field evolves for sure. With using stellar polarization and combining that with Gaia distances, we can actually start to make reconstructions of the magnetic field in 3D instead of having to rely on really analytical, ad hoc models of the galaxy's magnetic field. And finally, I showed you one example of how we're trying to constrain the magnetic field properties of nearby features in the ISM. Okay, that's it. I'll stop. Any questions?
Great, thank you very much. Okay, we've plenty of time for questions and discussion. So if you're in Zoom, please raise your hands, electronic hands, so I can see them. I think the Virginia conference room, I don't see it here because all the postdocs are around the world. Anyway, all questions here. So Moa, please.
You showed the 3D map of the Radcliffe wave from the PhD student. So are those models, or is that based on the stellar polarization data?
No, so what we're doing now is assuming some 3D geometry for the field. What does that give us in the projected polarization? So what would it predict for the polarization of the stars, and then do like a comparison.
Right. And does he, sorry.
Well, you're assuming did you say a 3D geometry?
Yes, so what happens if you assume that the magnetic field in 3D is following the Radcliffe wave, or if it's having a tilt with respect to the spiral arm? How did that project on the sky in stellar polarization?
Mm-hmm. You have Zeeman as well, don't you? So can you...
Unfortunately, very, very few, and actually not in that part of the sky.
Really, all the pulsars? Can we do pulsars, Zeeman?
Zeeman pulsars.
No, sorry, not Zeeman pulsar. No. Sorry, not Zeeman pulsar. But you can do dispersion measure to pulsars.
Yes. So the issue with the Faraday rotation is that it's an integral. And it's weighted by the thermal electrons. So it's tracing a different phase than what the dusty, cold ISM is. Mm-hmm. So it's kind of tricky to rely to get the line of sight component from Faraday and then the plane of sky from stars.
Mm-hmm. And you're saying Zeeman is too sparse?
There's no... Unfortunately, this part of the sky was not covered by Arecibo. So no, there's actually very few, if any.
Mm-hmm. So back to you had a follow-up.
You asked my question.
Oh, sorry. Well, Lee, I see you have a question, please.
Yes. Yes, I your argument that the magnetic field is along this wave. So I can see in a plane of sky, the background polarization seems to follow roughly the direction of that wave in projection, right? So it's the argument that because you actually know the wave, which portion is coming towards you, which portion is coming away from you, and then you use the Faraday to get the line of sight, and that seems to agree with the geometry of the wave. Is that the argument?
So no, we haven't used the Faraday rotation. Let me see if I have a hidden slide somewhere. No, unfortunately not. 1 second. Might be here. Yes. I think this might clear things up. So if you look at the, oh, come on, where are you? Here you are. No, okay. That's not good. No, don't leave the meeting. Okay, if you, hopefully this will show up. There's a lag. Okay, let's see here. Where did I find it? Here it is.
We can see it.
Yes, we can see. Okay, so, oh dear, what did I do? The stellar polarizations have a different properties as you go from the place where the magnetic field is close and projected on the sky to the place where it isn't. So here, I can try to do this. The vectors that I'm using, the length of the vectors is proportional to the polarization fraction. The vectors are longer where the magnetic field is in the plane of the sky, and they're shorter where the magnetic field, where the spine of the Radcliffe wave is pointing away from along the line of sight. So there are two things that you can do with a stellar polarization. You can look at the amount of polarization as a function of the location on the wave. You can also look at the dispersion of the angles as a function of the location on the wave, and both would indicate, at least they're consistent with this change, something coming more along the line of sight than in the plane of the sky, and then again in the line of sight. Does that clear it up?
Yeah, okay, that's great. So you're saying that just by looking at the dust polarization property itself, you can get both the plane of sky alignment, the orientation, but also some sense of the bending of the field in the line of sight.
Yes,
Okay,
correct.
right. But one maybe sanity check would be that if there is polarization, in the general region, and if you can be sure that these are actually due the Faraday rotation, if that from that feature, you may also get additional check on that, I think, right?
Yes, for sure. And that's actually, this has been known for a long time. So Hylas back in 97 did a similar analysis with fewer data, and he found that these points here at latitude 75 and then longitude 75 and then longitude 200 or so, those had a minimum of the polarization fraction. And from that, the Faraday rotation people said those are the locations where we should find an excess in the Faraday rotation, and indeed that's where they find it. And so that was baked into all the then models of the galactic magnetic field. So all of the models know that towards this location and towards this location, there's an excess of Faraday rotation. Now, what we're finding that's different is that there's also this a deviation from the midplane of the galaxy. That's it.
Okay. I do have another question, but I'll let other people ask first.
Well, let me just try and follow up on that. So, is the general idea then that there's one coherent field flowing along the Radcliffe wave?
That's what we think.
There's no field reversals within this scale?
There is no data that indicates a field reversal in this spiral arm.
Right, and this is sort of a spiral arm, but it's very straight.
It is.
So is it straight because of the magnetic field? Well, what's the magnetic energy density in this relative to other forms of pressure?
Good question. So from very early works, we know that the energy density should be order 1 eV per centimeter cubed, and that comes from estimates from there was Kulkarni back with the pulsars back in the 80s or 90s.
But is that the diffuse ISM or in the
diffuse ISM?
Right, but the mean density here is higher, right?
That's true. We haven't done an estimate based on, well, the only thing we could do was Davis-Judson, like our Fermi type of estimate, and we haven't done that because we want to be really careful of what densities we assume, what velocities we assume, and all that.
We have the 3D dust maps.
Yes. So that would be the plan for the next, to get the strength estimate as well. For now, we're only focusing on the geometry.
But there's some famous giant molecular clouds as part of this structure. You don't see the field becoming more disordered in the GMCs if they're self-gravitating.
So in Orion it does, in Taurus it doesn't. It depends.
Okay. Lee, we can go back to your question. I don't see another question yet, so go ahead, Lee.
Yes, this may be more of a comment because it said that this feature, at least the feature that you're mapping, is maybe about 100 parsecs, right? And that reminded me of another feature, which is the galactic bones, and there are actually a lot of Sophia polarization data coming from people like Ian Stevens. I wonder, that will also give you sort of magnetic field orientation relative to elongated galactic bones. I wonder whether you actually looked into that or have any insight into that.
I haven't, but I'm really curious to see what they find. I know that there are several surveys targeting these very dense filaments, but I haven't seen results yet. Are they out? Do you know?
I've seen some, mostly just because I was on the collaboration. But you can email Ian. I'm sure he'll be happy to share the results.
Yeah, that'll be cool. Yeah.
Well, so coming back to the Radcliffe wave, then, so what is the wavelength again, and what are the theories for explaining the wavelength, and does it relate to magnetic field strength and the Parker instability?
Yeah, so The wavelength is around a kbc. The total length is around 3 kbc. The first sort of theory or idea was that there was some disturbance of the disk caused by some like dwarf interaction. People looked at the stars. So stars with different ages show different types of perturbation. The older stars in the disk do not show a perturbation in their kinematics. The younger stars do. So that would point away from the local perturber, or at least it gives you a time scale. And then another sort of idea is that it's just some random feedback, happening to have some minimum and maximum at the right points exactly to form a wavelength pattern.
What kind of feedback would be strong enough to?
You need to have some clustered supernovae go off and there and below and somehow like that. For the magnetic field, the thing that we came up with was the Parker instability, but of course we have to look at more of the parameters to see if it's if we can rule it out.
But in the Parker instability, if I remember, when you're far away from the mid-plane, you're low density, and it's buoyant.
Yes, it should be.
So is the density?
Here you do have Orion, which is sort of low, which wouldn't work that. Although there is other material that is not seen here in the very dense star-forming regions that seems to be extending way, way higher than the plane. And the kinematics would imply that there is some motion along the field lines there.
So the field map goes beyond the actual dense region, does it?
Yes, so there's more dust. I don't know if we can, I don't have a slide here, but so part of the North Celestial Pole loop that has a lot of H1 emission also goes way above here. But it's I mean, the kinematics there are really debated. Some people said that they found oscillatory motions. That was proven not to be the case. So yeah, if we don't know the kinematics, it's kind of hard to say, I think. Yeah.
Very, very interesting.
There is a question.
Oh, please. Yeah.
So do you only see the Radcliffe wave in this local arm, or is it in other like spiral arms too?
Yeah, so this is the most clear indication of this wavy pattern. Let me go, there was a paper that said that also this feature here appears to have a wavy pattern. And if you make a cut through here, you also see some sort of wavy pattern. So at least in one of the papers, it was claimed that it might be a more common process than just one portion of a spiral arm. But I haven't seen a follow-up on that.
Okay.
Is there any hint that any of the feedback bubbles, H2 regions, or might be magnetic influenced by the dynamics of the field? So
How would you mean?
Well, maybe expand. In the H2 region, maybe the expansion is easier along the field lines.
So you would see, so one, that's tricky because, okay, for the local bubble, for example, we know that the magnetic field, at least in models, is mostly parallel to this direction. And with that kind of logic, you would expect the bubble to be more elongated along the magnetic field, but the problem is that you have a higher density of the midplane. So that wins out, and then your bubble is elongated like this, perpendicular to the field lines instead of parallel, because of the increase in density in the midplane compared to the higher up. So, and I'm not sure if other H2 regions show that. I would have to look. That's a good idea.
I'm thinking, maybe Lee knows about this because, Sam Crowe, who's a former Avico student here with James Webb, has found these bracket alpha filaments, ionized filaments, very linear in the galactic center, suggesting strong fields. So I don't know if there's any H alpha maps that might be useful. Lee, have you thought about this at all?
Well, I think in the Sam's case, the No, this is I think it's the bracket gamma filaments, right, in the H2 region.
Bracket
And
alpha, I think.
it's that bracket, yeah, but in any case, it's just you have the observation of this emission. It seems to follow the magnetic field. And he's actually, his senior thesis is actually doing simulations to show that with, strong enough magnetic field, maybe 1 milligauss, you can get kind of the features like this. So he's actually writing this up. So yeah, I mean, the strong magnetic field definitely could explain the features in a very broad sense. But I actually had another question for Gina, even though this may not be related to this particular presentation, but I did see there is a map for the Polaris, I think, in the relative diffuse region. It always struck me that the polarization vectors are so uniform in at least in the lower density part. So my question, probably general question, is that an indication that magnetic field is really dominating, the dynamics, at least in that kind of environment? I don't know whether that region is the co-neutral medium or it's actually sort of become molecular.
Yeah, so it's a translucent molecular cloud. So you're in that phase transition between atomic and molecular. So yeah, at least when we did the DCF analysis for these two regions, we found that indeed it's a dynamically important field. But this is like for the majority of the nearby, molecular gas at these kind of densities, Planck showed that these ordered fields are really common. So I don't think I don't think that Polaris is an exception in that case. It's when you go to the denser regions that this very large scale orderedness seems to disappear, at least for the nearby star forming regions that I've seen.
So does this mean that this part in the box A is really magnetic dominant in probably most sense, right? Dominating maybe the turbulence, maybe even the gravity. So in that case, it'll be magnetic subcritical. Would you actually claim that the box A is magnetic subcritical, cannot form stars on its own?
Oh, yeah. So this cloud isn't forming stars. There's like one core in box B, so it's definitely subcritical.
Mm-hmm. Well, I want to remember we should look at the H alpha maps carefully to see if there are any ionized filaments that might correspond here. But in terms of the kinematics along the Radcliffe wave, then, is it large enough that you're probing different galactocentric distances that you'd expect, differential rotation shear due to the rotation curve of the galaxy? And is the magnetic field influencing that? I mean, can you see that process happening?
So there was a paper, I think, a few months ago that, it was 6 months ago that claimed that the Radcliffe wave kinematics would imply that it's oscillating up and down the midplane. And then there was another paper that said, no, if you actually include shear, this thing is not going to remain as it is. There's no time for it to oscillate. It's going to rip apart. So that's as far as I can tell. But for including the magnetic field effects, I haven't thought of that, actually.
Mm-hmm.
Do you think it would have a stabilizing effect?
Well, without the field, I mean, things just shear around, and then the field just ties things together more. And so, I assume you'd be slowing down the inner orbits and accelerating the outer orbits, maybe. One could try and look for the kinematics.
It would depend what the magnetic pressure is doing compared to the shear.
Mm-hmm.
I don't know if the energies would be comparable.
At some point, the shear will win. But
yeah.
Okay,
good
so
idea.
we should think about it. Great. I have one more question. Are there other questions? Does any of your analysis depend on grain alignment physics, like the amount of, you're just doing field direction, are you? But it's integrated along the line of sight. So you're weighting by normally, emission or density or something. But then grain alignment might go into that weighting. So,
Yes, but I think for the diffuse ISM, we don't expect grain alignment to vary that much. I mean, sure, if you're very near a OB star, that would change. But also for now, we haven't really used the polarization fraction, which encodes the information about the alignment. We're mostly using the dispersion of the angles, and that.
right, but your overall angle is an average along the line of sight, so it's more the weighting of where it's coming from.
Yes, but my feeling is that because the density of this structure is so much higher than the surroundings, even if you had a change in grain alignment, which I don't think you would at these range of densities, you would still have the Radcliffe wave dominate your signal. Does that answer your question, or did I
No, I
go
think so.
somewhere else?
So its call density is really dominated by this feature, but
Yes.
on certain scales, eventually you'll, as you go away from it.
Yeah, perhaps. Although, to change the alignment efficiency, I think you would need to be very near some localized source, right? Otherwise, you're just in the diffuse radiation field. What's going to change? I'm not sure.
I'm trying to remember, if you have this anisotropic radiation field just because you're above and below the galactic plane, can that have an impact?
The strength of the radiation field would presumably change. I have to think about it. I'm not sure.
Okay, any last questions for Gina? Okay, if not, let's thank Gina again for a great talk and discussion.